So it's my great pleasure to invite Manolis to our workshop. He's an assistant professor in the School of Computing Science at Simon Fraser University, and his work focuses on analysis, organization, and generation of 3D content. So it comes from a very interesting place, and I'm really excited to hear the work that you're doing and how it relates to how we do 3D representations. Thanks very much.
Thank you so much for the kind introduction and for inviting me to speak at this workshop. And thank you all for attending this talk. So my background is actually in computer graphics and 3D computer vision. So this will be coming from a slightly different perspective. And I'll begin by describing a little bit of my brief history of how I started to work in this research direction, and then conclude the talk with a few quick snippets of recent projects that I think describe some challenges and opportunities. But before I do that, let me say a little bit about the title here. I'm using some fairly, specific terms, and especially since I'm coming from a different background, I'd like to share my, definition for some of these terms. So beginning with, this embodied AI in the title, right, in quotes. What do I mean when I say embodied AI? This is recognizing the central role of embodiment in the emergence of intelligence. So there's this embodiment hypothesis that intelligence emerges when an agent interacts with an environment as a result of that agent's sensory motor activity in the environment. And this is actually coming to us from cognitive science, right? This is studying how human intelligence emerges, right, in human infants. So embodied AI, recognizes this embodiment hypothesis, its critical role in intelligence. And it involves a study of, embodied agents, right? Familiar things, perhaps to most of you in the audience, robots that are physically embodied in the world and take actions in the world, like this robot participating in the DARPA Robotics Challenge, attempting to open a door. And research, in this direction, it studies questions like, how do we develop computational systems that exhibit human-like intelligence in terms of their ability to actively perceive the environment, to do some sort of long-term planning in the environment, and also to learn how to do these things by interaction with the environment. So, this is, embodiment, embodied agents, research studying them. Now, if I were to, take agents here and strike it out and put robots here, this should sound very familiar, right? Robots. But why do I use this term embodied AI, embodied agents? It's because I want to focus a little bit, shift, this from, when I say 3D simulation for embodied AI, shift it from physically embodied agents that are taking actions in the in our real physical world to this other setting where it's more about virtual embodied agents taking actions in a virtual world. So this is really the 3D simulation part, right? Simulating scenarios where we have embodiment and environments where these embodied agents act. So this is the definition for this term, studying virtual embodied agents in virtual worlds. And this direction of research, when I first started to engage with it, this was around 2017, 2018, and started to do work in it, there was this explosion of interest in various kinds of simulation platforms, especially for indoor environments. Here I show a few examples from that era, around 2017, 2018, focusing on either synthetic data sets of interior environments or scanned, acquired real-world indoor environments. And this is by no means an exhaustive list, right? There's quite a bit of activity at the time. Various groups, constructing these simulation platforms and data sets to do, essentially this kind of virtual embodied agent experiments. And it's no surprise that there's this much interest, because you can use these kinds of settings for a variety of tasks, and you can leverage them from a variety of perspectives, different communities. Here again, just a few examples, by no means exhaustive. Visual navigation tasks, simulating robotic grasping, studying grounding of natural language, which is of increasing interest nowadays, as well as grounding of instructions, following instructions to navigate within an environment or manipulate the environment, change the state of objects and such. So quite a lot of interest. At the same time, what was interesting in the common approach to constructing these simulation environments and the content that goes into them was that they relied on essentially this black box strategy of taking an existing 3D game and the content that goes with that game and constructing out of it a platform for the purposes of research. So just to sketch it out, it looked largely like this. Take a Unity game, write a Python wrapper around it that can interoperate with this Unity game, send keystrokes and receive, like sensory input, essentially frames that were being rendered, and then hook that up to a learning framework, right? Say PyTorch, TensorFlow, and such, so that you can, run your experiments on top of this. And this is, of course, nice in that, it allows us to leverage these, game engines that were already available and the content that goes into those games. But it's also not necessarily the best idea if we care a lot about efficiency. So typically, these game engines operate at rates that are designed to, show visuals to people, right? So this is in contrast to the fact that, we're using this for a very different use case. We're not really taking this game and showing it to people, right? We're not in this setting where we're rendering for a person, human eyeballs to look at on a monitor, right? At say HD resolution at 60 Hertz. But instead, we want to use the simulation platforms to, generate data and feed it into some, maybe learning-based method for doing navigation or manipulation. And there we care about some things that are very different, right? Maybe we don't care as much about, high resolution visuals, but we care a lot about the, how quickly we can generate that data. And we also maybe care a lot about what kinds of modalities are available to us. Not only do we care about rendering, RGB pixel values to display on a screen, but maybe we also want to simulate, say, depth information or surface normal information or audio or, have a simulated, LiDAR sensor. So multiple modalities and as fast as possible, ideally. So there's a contrast between these two scenarios, and that was essentially the motivation with which I entered this research area. And maybe the first major work in this area that I was involved in was called AI Habitat, and it asked this question of, can we do better, right? Can we do better if we realize that there are these two different scenarios? And it focused on primarily these kinds of visual navigation settings in somewhat high fidelity reconstructions of indoor scenes like the ones that you see here. These were scanned environments that were used as the data to power this simulation platform. And then with a little bit of attention paid to how we engineer the software stack that renders the sensory input from these environments and then simulates the agent navigating, we showed that you can actually do far better than what was common at the time, right? You could get orders of magnitude of improvement in the speed at which you can simulate these visual navigation episodes. Now, at this point, maybe some of you may ask, why focus so much on the speed at which these simulation platforms can run? And to answer that question, I'll give an example from a couple of papers at the time. These were papers that emerged at the time that this work was being done, that were studying this question of comparing learned methods for visual navigation to classical stacks, SLAM and navigation stacks. They were interested in this question of how do these compare in some of these indoor environments. And the conclusion that these couple of papers reached is that the classical stack does pretty well. We have some way to go to leverage these fully end-to-end pixels to actions kinds of learned agents. They were outperformed by a classical SLAM plus navigation stack. And both of these relied on roughly, let me put it very roughly, 5 million steps of experience in these simulated interiors to make that conclusion. This was what was practical, within about a week of running experiments on hardware that was common at the time, on the software platforms that were available. Now, if we try to plot what that looks like, here I'll just try to summarize it very briefly. The trend is what's important. On the horizontal, we have the amount of experience that's provided for these learned agents that are navigating in interior environments. And then on the vertical is a summary metric of both success and efficiency at navigating. Higher is better. So if you're close to the top, you're highly successful going from point to point, and also very efficient, very close to the shortest possible path. Now here you see a green line, which is the traditional stack, which doesn't involve any learning, right? So it can be applied directly. And then you see various lines for agents that were trained using reinforcement learning, from pixels to actions, and agents that have different modalities available as input. So RGB and depth, a blind baseline, which doesn't have any visual perception other than knowing how far away and in what direction the target is. And this was essentially the conclusion from those last couple of papers, right? SLAM, better than these RL agents. But if now we can leverage a platform that allows for experiments to be done orders of magnitude more efficiently, we could allow the amount of experience to be significantly larger. And for this particular setting, we actually begin to observe that at a certain point, the trend reverses. And some of these RL agents begin to outperform this SLAM stack. So this was interesting, right? Making larger volumes of data generation more practical actually allowed for different conclusions to be reached. That I think is one reason why it's important to care about efficiency, but it's practically important for researchers. Of course, this was from quite a while back and was only a first step in this direction of working on simulation platforms and associated datasets. In more recent work, we tried to push a little bit farther, make these kinds of simulators go even faster, leveraging the idea of large batch simulation. And I'll very briefly describe here what I mean by that. This means, recognizing the fact that often it's possible to simulate in parallel many possible, agent rollouts. And if we take a batch approach to this, we can reduce inefficiencies even further. We can batch, the rendering of the state of the world and batch the evolution of the state of the world, and then, use those large batches to do learning and inference. And what this looks like roughly is, having this, essentially composited frame of 128 agents being rendered at the same time, navigating this world at the same time. And this allows us to, again, gain order of magnitude improvements in terms of the overall performance, the speed of this simulation platform. So this, I think, direction of work articulates what I believe to be an emerging challenge in leveraging simulators, and that is to design simulation platforms that are efficient, especially in this setting where there's this GPU cohabitation. And what do I mean by GPU cohabitation? I mean the fact that nowadays there are various pieces of software that we want to be efficiently running on a GPU device. We want to render, that is to create the sensory input that would go into a particular agent. We also want to evolve the state of the world. So we want to maybe simulate some rigid body physics or otherwise change the state of the world. And at the same time, we also maybe want to have a learning framework that consumes the data that is produced by the other two components and optimizes the parameters of a neural architecture. So these three, they cohabitate on this GPU device. They leverage its resources, and paying attention to how data is being exchanged between them, at what frequencies, and how all of this is staged and scheduled can actually lead to even bigger improvements in efficiency. So that, I think, is one research challenge for anybody who's interested in working in this stack of simulation. There's another challenge too, and to describe this other challenge, I'd like to go back to earlier when I was motivating this direction of embodied AI and the embodiment hypothesis and interaction, and make the point that everything that you saw from those visuals earlier is frozen in place. These high fidelity reconstructions of real spaces are all just a static, completely frozen surface mesh representation with acquired, surface appearance information. So we actually don't really have much interaction here other than this, movement through space. And this stands in stark contrast with, an earlier point that interaction is really important, and interaction is really where it gets tricky, right? As this again video clip from the DARPA Robotics Challenge shows, opening a door in the real world, that's pretty challenging. Perhaps far more challenging than reliably navigating through free space. So how do we study this set of problems that involve interaction with simulation? One strategy is to have professional artists create for us interactive versions of these acquired real interiors. And this is in fact a strategy that we took with the Habitat 2.0 work from a couple of years ago, where professionals looked at these reconstructions of real spaces and then designed synthetic versions of them that could be interacted with, where the objects can be moved around and you can open the cabinetry in the kitchen and so forth. And doing that allows us to now have some degree of interaction, have a mobile manipulator like the one you see here, go into this kitchen, open the drawer, and then put an object inside of it, and then generally just rearrange the state of the environment here. And with this support for interaction, for manipulation, we could then study some of these settings that require object manipulation. And in here, I'd like to make just one high-level point. The specific details of the results are not particularly important, but the point that I want to make is that we have a long way to go for these embodied AI agents in settings where interaction is required. Even in simulation, where there's not much noise, many things are idealized. So here you see a plot, you will see a plot where on the horizontal axis, there's the number of interactions that the agent is required to do in terms of picking up objects and placing them somewhere else. So this is a sequence of pick and place operations. And then on the vertical is the success rate, right? How long, how successful is this agent at carrying out this sequence? And here there's a set of families of approaches of agents that are being compared, these monolithic RL agents that take pixels and then output actions, and then some more traditional sensing, planning, and acting pipelines. So again, the details aren't super important, but generally what I want to show is that these start out high, but very quickly performance degrades, and for many of the approaches, degrades fairly badly when we have longer horizon pick and place manipulation. So long way to go. And here a point that I would like to make is that especially if we care about these experiments where we want to generalize to new instances of objects, new layouts of the environment, it's particularly important to care about the data that is being used here. And one detail from this description earlier of this replica CAD, this interactive synthetic version of a real environment that I described, is that it's actually composed of only 6 scenes with pretty much exactly the same architectural layout, and the objects just perturbed, moved around. The furniture pieces, you see a top-down view here, are just moved around in this exact same space. And moreover, all of the objects that are available, their count is 92. There are 92 objects. So there's maybe like, a couple of fridges and that's it, right? So it's very hard to, to say, oh, can we train something that will generalize well to different settings, even just within simulation, if this is the regime of operation. We're working with only 6 scenes and 92 objects in those scenes. So how do we, move in a direction that allows us to alleviate this? This is where I'd like to very briefly talk about some recent projects that aim in this direction towards creating larger and more interactive 3D scene datasets that we can use in simulation. The first project essentially adopts this strategy of going from something that we have a lot of to this other resource that we don't have much of. So going from floor plans and photos in those floor plans to 3D scenes, digital 3D scene representations. It's this project called Plan to Scene from CVPR a couple of years ago, and the visual here explains the goal. We take a floor plan with a small number of photos that a person took in that floor plan, and then we convert it to a 3D scene with appropriately textured floors, walls, and ceilings, and so forth. And now we can have a much larger volume of these indoor 3D environments within which to navigate and do other tasks. So that's one project, but all of this is of course static. What do we do about the interaction part? Here's another recent project that focuses on leveraging, again, something that we have a lot of data for to create something that we have less of. So going from 2D videos to 3D articulated objects, more specifically going from videos of people interacting with articulated objects, like the example that you see here of a person opening the door on a fridge, and reconstructing out of that an articulated 3D object, the representation of the fridge and the door. So this is going in the direction of creating a lot more articulated, interactive 3D objects. Another recent project, which again relates to this direction of creating more interactive 3D scene datasets, leverages this idea. Going from multiple observations, multiple scans of a space, of an indoor environment, to an articulated, an interactive version of that 3D environment. So it's this project called multi-scan to reflect the fact that we are scanning an environment multiple times. And it's relying on the development of a pipeline that allows us to efficiently capture a room multiple times, right? To go into a room and scan it once, twice, 3 times, to collect that, reconstruct it, create a high fidelity textured 3D mesh representation, and to semantically annotate it. And to use this pipeline to create a data set of such annotated 3D scenes where we know all the objects, all their parts, and how they articulate. And then lastly, to leverage that data set to create a benchmark for some important, I would argue, perception tasks: object instance segmentation, part instance segmentation, and in particular, part mobility estimation, estimating how the parts of common indoor objects can articulate. Now, this is a data set that is available for any of you who think it might be useful. It provides 100 or so environments where all of the objects and their articulated parts have been annotated and can be used within simulation platforms. And then lastly, in parallel to this, I'd like to describe a very recent project that creates more realistic synthetic 3D scene data sets. And this is the project called Habitat Synthetic Scenes Dataset, HSSD for short. You see some example visuals here. The goal of this was to create a larger volume of synthetic 3D scenes that better conform to the statistics of the real world, right? The layout of the objects, the appearance of the objects, hopefully better than the regime of operation that you saw earlier with Replica CAD. And this was focusing in particular on the realism aspect, which I'll motivate very briefly here, by studying how important it is for these synthetic scenes to be realistic in terms of layout and appearance. Here, what we did is we took this new dataset, HSSD, compared it to procedurally generated scenes from recent work, Proctor, and then trained agents in these two and deployed to the higher fidelity scanned real world environments, HM3D-SEM, that's the third column that you see there. And if we plot what happened here in the horizontal axis, we have the number of training scenes that was used for either one of these synthetic datasets, either Proctor, which was procedurally generated and very large scale, or HSSD, which is smaller scale but more realistic. starting with a few scenes, we have comparable performance. But if we begin to use more scenes, eventually we reach a point actually where a few highly realistic HSSD scenes lead to significantly better generalization performance than many, many more orders of magnitude of procedurally generated synthetic scenes. So this, I think, it is showing that realism is important when you care about, leveraging simulated indoor environments and then generalizing to something that is a little bit more realistic. Very briefly, I'd also like to advertise the Home Robot Challenge. This is a competition that is ongoing and will have a component organized at New RIPS 2023. It's focusing on open vocabulary mobile manipulation. So this stretch robot platform in both simulation and in reality. The simulation component is relying on this HSSD dataset that I just described. And the task is essentially this, manipulation of an object from one, picking it from one location and placing it in another in an open vocabulary setting. So for those of you who are interested, definitely check this out. The challenge is open. And that's where I'd like to conclude. So just a few quick takeaway messages. Firstly, simulation, I would argue, is quite useful. It allows us to do things efficiently, at scale, more safely than, of course, real deployment. But even though it has all these beneficial properties, it's unwise to treat it as a black box. Sometimes there are significant gains that can be had by just, briefly looking at what is inside this box, right, and trying to optimize it a little bit. There are a few open challenges on the, side of simulation platforms for embodied AI and for robotics. Doing this efficiently such that we can have data-hungry learning approaches be, feasible to experiment with, and also simulating dynamic scenes. These are open challenges. These were the two main challenges that I tried to articulate. And the key bottleneck, definitely for the latter, is the amount of available interactive 3D scene data sets, right? And that's something that I'm hoping we can, focus on as a community. And then lastly, this area of working on the 3D scene data sets and the simulation platforms that power, the various experiments that people can do with embodied AI and robotics, I think it's an area that offers many opportunities for high impact work. It enables downstream research in vision, robotics, machine learning, AI broadly construed. And if any of you are excited in opening up that black box and or collecting more 3D scene data, I would strongly encourage you to work in this area, and I'd be happy to chat. So I'd like to end with just a quick acknowledgement to the students and collaborators who, of course, did all this hard work, and I'm just here, telling you about it. And I'm happy to take any questions.
Great. Are there questions in the audience?
Thank you for the great talk. So from your talk, it seems like for the interactive scenes, there are three different types, like articulated objects and like small objects where you can just move easily. And then maybe there are scenes where you can just see big objects difference. So to me, when I look at these researches and simulations or maybe data sets, it seems like there are three different streams of these three different concepts. Do you think there will be any like data set that combines all these, and maybe we should, whether we should approach these problems as a single problem later? Like, I was just wondering what's your opinion?
Yeah, that's a good question. Yeah, thanks. Yeah, so definitely there's these, different aspects of what it means for a scene to be interactive or for it to be dynamic in some sense. Rigidly moving objects, right? Objects that can exhibit state change in terms of their parts, right? And there's even more complex things like highly deformable objects, right? Cloth and even liquids, right? That's another I would say direction as well. And I think the last one you mentioned was maybe appearance, or material changes, something along those lines, for even for furniture objects, large objects. Yeah. So each of these, I think, in an ideal world, we would be able to tackle all of them together, but in reality, I think we can focus on each of these aspects as, specific, directions in which we can push the frontier. And it's good to do so because we can, build essentially on these parallel streams of work, right? If we have more, data of rigidly moving objects, we can combine that into a synthetic 3D scene. If we have more objects for which we have information about how their parts can move, again, we can leverage it, to create 3D scenes. If we have more detailed models and ability to simulate, highly deformable objects or liquids and things like that, generally we can combine it, with, other things. So it makes sense to me to work on these as parallel streams and then, utilize things, to compose, richer, more dynamic scenes. So doing everything at the same time, I think would be probably a little bit too challenging. Yeah.
Thanks for your talk. And I'm a super fan of Habitat and the Metaverse 3D. I have used it like in the past 2 years a lot of times. And so my question would be from the user side. So like I'm wondering like if you have any plans to like add features for object state changes, like very similar to the like AI tutor, like their simulator stuff, because like this kind of feature would be very helpful for a lot of like high level embodied AI tasks, like like some object maybe like cooking stuff in the simulation. For example.
Yeah, that's a good question. Yeah, so these state changes, right, that involve, say, something being cooked or something being cut, right, chopping the onion, cooking it in a frying pan. These are also very interesting, right, and yet another challenge in terms of digitally representing the what the dynamics of the real world are like. So I think the question was, any plans for Habitat to involve these kinds of things? In the long term, yes. In the near term, not so much. This is all very challenging to do well, right? And I would say, it's nice that the community has various platforms. Some platforms focus on this very specifically, right? Having, simulation platforms that allow you to undergo, these kinds of more complex state changes, and then studying, problems about planning, that involve, cooking objects and such. AI tutor is a great example. So for folks where that is really important, I would say AI tutor, great resource, right? For folks who are more interested in, maybe, higher fidelity, scanned environments and, simple things like rigidly moving objects and articulations of those objects, I would say maybe, the Habitat stack is a more appropriate resource. So yeah, in an ideal world, everything could be combined, but again, I think it's nice that as a research community, we can move in parallel and make things possible. Yeah.
All right, in the interest of time, can we save the questions for the panel discussion, which will happen after this? So please join me in thanking Manolis.